Good day, everybody, and welcome to our webinar titled Describing the Nonlinear Phenomena in Optical Fibers Using OptiSystem. My name is Brian Tipper. I'm the VP of Sales and Marketing at OptiWave, and I'll be sitting alongside your presenter, Mohammed Abusaif. Before we begin, let's discuss the format of today's webinar. During the presentation, we're going to have two Q&A periods, the first one at the halfway point and the second one at the end. We're not going to be taking any questions via the raised hand option, so please type all questions into the questions section only. We're also going to launch 3 polls, such as the one that you're viewing now. Please take a moment to answer each one. And over on the GoToWebinar control panel, you'll find a PowerPoint handout. You can download this at any time. And finally, we're going to be recording the webinar and distributing it to all registrants via download link that you'll receive in an email approximately 2 hours from now. With that said, I'm going to go ahead and hand over the webinar to our presenter, optical engineer, Mohammed Abusaif.
Hello, everybody. Thank you very much for joining us in this webinar. This webinar will be on nonlinearity phenomena in optical fiber. I hope you find a lot of beneficial information in this one. So let us start with the outline of the webinar. As you know, the nonlinear phenomena in optical fiber plays a crucial role in optical communications. So it's very important to understand each phenomena just to be able to design an efficient optical communication system. So in this webinar, for the introduction, we just a brief description just to refresh your information, your knowledge about the source of the nonlinear phenomenon optical fiber. And after we'll study and we'll revise 7 nonlinear phenomena. The first example will be about self-phase modulation. The second, cross-phase modulation. The third one, self-steepening. Fourth one, after self-steepening, we're going to take a short break. And after, we'll continue with the fourth one about 4-wave mixing example. The fifth one, release scattering and stimulated Raman scattering, and we'll end up with stimulated Brillouin scattering. We will have a webinar summary after all these examples. Okay, so if we start now with the origin of the nonlinear phenomenon in optical fiber, as you know, optical fiber has a very short cross-section area and the light launching inside it. Due to the high intensity, the electric field produces polarization inside the the optical fiber. This polarization is proportional to the electric field in different ways. The first one, the polarization is proportional to the electric field directly, the electric field square, electric field triple, and so on. So for the first one, this is the linear effect, but after this one from chi3, you will have the nonlinear effect. For optical fiber itself, so let me first explain the parameters for this equation. B is the polarization, epsilon is the permittivity of free space, susceptibility of the first order, second order, third order, and E is the electric field. For the electric field, the optical fiber, for silicate optical fiber, size 3 almost equals 0 due to the structure of the optical fiber, and the only one, the lowest higher order susceptibility is Xi 3. This is the main reason for the nonlinear phenomena. The relation between this the nonlinear effect N2 and Xi 3, it's given here, it's written in many literature, and the total refractive index would be the linear one plus the nonlinear one times field intensity. And as you know, the value for this N2 for the fiber is very low. It's about 3.2 10 to the power minus 12. Okay, if we start just to classify these different phenomena, as we said, we have different nonlinear phenomena. So the real part of Xi is responsible for self-phase modulation, cross-phase modulation, self-steepening, and 4-wave mixing. The imaginary part is responsible for stimulated Brillouin scattering and the stimulated Raman scattering. This scattering has 2 kinds. The first one The first one, it should be inelastic, so it means the generated signal has different frequency than the source itself. And elastic one, the elastic one is the release scattering. Release scattering, it's a signal that generate and it has the same frequency of the source itself. So these like different categories of the nonlinear phenomena and the main cause for each of them. Okay. Let us start with the first example, with the first nonlinear phenomena. So the cell phase modulation, just let us explain the physics without equations first. Cell phase modulation, it means we have a very intensive signal. It might be a CW or it might be pulse. And this high intensive signal, it changes the properties of the medium of propagation. And as a result, the medium of propagation come back to the propagating signal itself and they make the spectrum widening in the cell. That's why it's called cell phase modulation. How to model it? For sure, there are many references. I just select one, the most famous one, it's Agrawal. So it's written here. So the variation of the field itself is proportional to the intensity. And there is imaginary part. This imaginary part refer to the phase itself. Without this one, it would affect the temporal profile. But because this J, so we have an effect on the spectrum. And the gamma is a nonlinear coefficient. It's related to N2, as we explained in the first slide, for this, the nonlinear refractive index and the cross section of the fiber. And for sure, it's a function of the operating wavelength or operating frequency. Okay, let us start with this first example. Okay, here we don't have virus. We just try to access executable file. Okay, so this is our first example. If you see here, we have two layouts. The first one, I would explain the cell phase modulation. By the way, we have new component. It's called the nonlinear optical fiber. This new component contains all the nonlinear phenomena that we will explain today. So as you see here, if you look at this one, so we delete or we ignore the losses, we ignore the dispersion, we just focus on the nonlinear parameter just to be able to study each parameter separately. So if you look here, you are able to, as you know, you are able to check the cell phase modulation, cross phase modulation, self steepening. And here is the Raman scattering if you want to include the effect of Raman. And for the enhanced tab, you can include the Rayleigh scattering. You can include the Brillouin scattering as well. So for this one, we have only, we would start with cell phase modulation. So we'd only have one signal. And if we run it, as I said, just we have two layouts. The first one to explain the phenomena itself, and the second layout, we will explain the effect of this phenomena on the optical communication system performance in terms of quality factor, bit error rate, and eye opening factor. Let us go to the first one. So let us run it. It would take around 1 minute and 30 seconds. Okay. During this one, let me explain to you the structure for the new user. So as you know, we have this the main component, the medium of propagation, and usually you need auxiliary components like how to generate pulses. So we have this one optical Gaussian pulse generator. So you can define the frequency, you can define whatever you want. And this pulse generator needs user-defined bit sequence generator like to feed it with a certain bit sequence. And after we need to visualize the data, the results. So we have varieties of components. We have optical spectrum analyzer, RF spectrum analyzer, eye diagrams, and OTDR, optical time domain visualizer, because we have optical oscilloscope. Oscilloscope, it works in RF region. Optical time domain visualizer, it works with optical domain for laser sources. Okay, I think now it's we have different iteration in this layout. It reached to 24. So few seconds, we can see the result. We can see, just to remind you, two layouts. The first one, we will see the cell phase modulation. We'll see the spectrum broadening. And the second layout, we'll see the effect for this phenomena on the optical communication performance system. So now we are done, 30 out of 30, so we are done. Let us go to the first layout. The first layout, if you check here, the optical spectrum, if you check optical spectrum analyzer, so if you check here the optical spectrum analyzer, as you see these peaks, this widening, it comes from the cell phase modulation. So, and the number of peaks proportional to the accumulated nonlinear phase shift. For the second one, for the second layout, I designed to you, as I said, just I want to study the effect for this cell phase modulation in the optical communication system. So we have created 3 reports. One, the quality factor, bit error rate, and the eye opening factor. So if you look here for reports, you have 3 reports here. I will explain it to you an example how to create this one later on in this presentation. So as you see, as expected, the quality factor decreases with increasing the cell phase modulation. Cell phase modulation here is increasing by changing the power, of the laser source. It's relative process. So what you need to increase, the nonlinear effect. Nonlinear effect might be increased by the power, might be increased by decreasing the cross-section area of the medium of propagation, might be increased by increasing the length of medium propagation. Just I decided to choose the power here just to make the program to be fast, to be in a short time, to be able to see the results. As you see, as we said, the quality factor decreases, the eye opening decreases as well with the cell phase modulation, so it has a bad effect on the optical communication system. Okay, so this is the first one. Let's close it and continue with this one. I just summarize what we have. So this one, as we explained here, the structure, here we changed the power, and the power you can, yes, by the way, the power, okay. The power here, you can make a sweep iterations. This sweep iteration, you can define a linear, exponential, log, whatever you want. You can make it manual based on your experiment or your research study. So after this one, we got the result. So if you see here, this is the input spectrum and this is the output spectrum at different power level of the laser source. And as you see, and as we explained, so number of peaks here, number of broadening is proportional to the accumulated nonlinear phase shift during the propagation of the signal through the medium of propagation. Okay, so now after we're done with the first example, we'll go to the second one, cross-phase modulation. Cross-phase modulation, it's very similar to cell-phase modulation, as you know, but the main difference is that we have 2 signals. Cell-phase modulation, the signal itself affect on itself, but here we have 2 signals. The first signal, it changes the properties of the medium of propagation, and the medium of propagation affects the second signal. That's why we have a coupled of equations. As you see, A1, A2, amplitude of the first signal, amplitude of the second signal. Gamma 1, it might be at the same frequency or different frequency. For sure, it would be a different frequency, the most important part. If you recall the first slide, this gamma, the nonlinear effect, is function of frequency. That's why we have 2 different nonlinear coefficients. And here is the intensity of the first signal, the intensity of the second signal. By solving these 2 equations, we can get the effect of one to another. Okay, let us start with this one. We will get the same message just because we are accessing executable program. Okay. So this one, okay, as the previous one, we have 2 layouts. The first layout, I don't want to repeat it, but the first layout just to explain the idea, and the second to check or to study the effect for this one on the system. I will only explain this one because it will be repetitive. For the second layout, I will leave it to you just to check it yourself. Okay, for this one, let me just run the program, and because it takes around 1 minute and 15 seconds, less than 1 minute and 15 seconds, and during this one, I can explain it to you, the layout itself. We have 2 sources, so 2 Gaussian pulse generator, optical Gaussian pulse generator, and we combine it with ideal multiplexer, and I insert here a delay time. this delay time just to make the two pulses separated from each other, or at some times they overlapped. Because as you know, the cross-phase modulation occurs when the two pulses or the two signals overlapped on each other. Otherwise, there is no cross-phase modulation effect. That's why I inserted this time delay, just to show you the difference when these two signals overlapped or not. And after we have the main component in our experiment, the medium of propagation, this nonlinear fiber, we have the auxiliary components here just to visualize it. We have optical spectrum analyzer, optical power meter, optical time domain visualizer. And as I explained in the first one, in the first example, this optical Gaussian pulse generator needs some bits to drive it. So we insert here user-defined. We have two kinds of bit sequence generator, user-defined, so you can insert whatever you want, or random bit sequence generator, so it generates random signals. Or you can like create whatever you want by inserting a MATLAB component or C++ component or Python component. Here, because okay, it should take less time, but because I launch the whole, I should, yes, I just forgot to tell you, we can calculate the whole project. If you choose this calculate the whole project, it means whatever layouts you have will be calculated. So we have here two layouts. That's why after the program finishes the first one, it starts to the second one. If you want just to focus in the only one of them, just make it active, open it, and after it choose the second one, calculate all sweep iterations in the active layout. So the program will calculate the active layout only. And we have different styles here as well. Calculate current sweep iterations, these options. If you want just to run the current iterations, you have different iterations. Here we have 30 iterations. If you want just to run 14, 15, 16, 1, so just to check the iteration you want and select the third one. So the program will run only this iteration on the active one. And the last one, calculate multi-thread all sweep iterations, the active layout. You know, it's the same concept as the multi-threading. If you have different calculation platform in your computer, so you can use this multi-threading just to expedite the process of calculations. Here I have another component just to check. It's as previous. I have the eye diagram analyzer. This eye diagram analyzer just to study the quality factor, to study the bit error rate, the eye opening factor. This is very similar to the self-phase modulation example in the first, in the few slides ago. Okay, we are now in 26 sweep iterations. So I just want to remind you, we have 7 examples. One of them we are done with it. So self-phase modulation. The second one is the cross-phase modulation. Now, as we said, we have 2 signals. One will affect the other. And the rest, we have another 5 examples after we're done with this one. I think now it's gone. It's done. So we are ready. Let's see what's going on. So this is the optical spectrum analyzer, the output. Okay, so let me explain to you what's going on here. So if we have optical time domain, so we have optical time domain after combining. So here, optical time domain. No, this is optical time domain visual. So, okay, so I have 2 pulses. Let us start from the first iteration. We have 2 pulses here. These 2 pulses are completely separated. So we have a very powerful one, and the second one, it's not as powerful as the first one. So as you see, this is the output spectrum. Don't forget this is the output spectrum. So just let me show you. This is the first pulse. It's around 1800 watt. I just make hypothetical value just to show the idea, but as I explained, it's a relative one. So, and if you see here, the fiber length, it's around 16 meters. So you can decrease this value and increase it to 50 kilometer or whatever you want. I just choose this number just to make it fast to be able to see the results. Okay, and the second one, it's around 0.06. It's very, very low power signal. As you see here, the higher power, the higher signal, I mean the energetic signal, has a cell phase modulation. But the second one, because it doesn't have enough energy, enough power to get the cell phase modulation, it doesn't experience this one. So, okay, let me show you also the input. This is the output. Spectrum 2, it's the output. Let me show you the input. So this is the input. This is the input 2 signals here. So if you compare it, the second one, the smaller one, it's the same. The bigger one experience cell phase modulation. Okay, after we make some iteration here, go to the fifth. So the second pulse go forward to the first pulse, the powerful pulse go to the second one, so closer to it. So, and as you see here, just keep watching this delay time. This delay, it's here now, it's around minus 43.043. So if I go to 8, so it's minus 31. Until now, there is no effect on the spectrum. Go to the 10, go to 13. Wow. So here, the two pulses start to overlap, and you see here the cross-phase modulation start to appear on the second pulse. This spectrum change is due to the first one. The spectrum change on the second pulse is due to the powerful pulse, the powerful first pulse. And if we go further, let us go step by step just to make it fully overlap. So you will see change of the spectrum. It's a symmetric one, and I make the delay continue. So after the second pulse, get rid of the first one, it crossed path. So the spectrum go back to its original value. So here they separated, and we got it the same one. So the cross-phase modulation, just let me summarize it. So the cross-phase modulation, a very powerful pulse or one pulse affects the medium, and the medium affects the second pulse. It causes spectrum broadening on the other pulse due to the first one. Okay. Okay, that's good with this example now. Let's close it and come back. Thank you. Let's close it and come back with self-steepening. Okay, here as usual, just to make it available. Yes, by the way, I will make all the material available to you after the presentation, or this examples, and even the summarize. You will see something interesting. I will make it available as well after the presentation. Here is the structure. Here is the fiber, and after the results, how to change it. Oh, by the way, if you don't have this nonlinear optical fiber, you can use bidirectional optical fiber for cell phase modulation and the cross phase modulation, and just uncheck the dispersion, and you can do the same examples as I did. Okay, so here is the properties. You can change it, all the properties, and here is the results when they are separated. There is no, this is the input and this is the output. Here, if I make it a little bit overlapped, you will see some change, completely overlapped signal here in time. I'm talking on time. Here is the frequency, here in time, completely overlapped, and you see this cross-phase modulation of the second pulse due to the first one. And here is the system performance as we explain it in cell-phase modulation. Okay, last example before the break, self-steepening. Self-steepening phenomena, it means the physical behavior of it. So if we have a pulse, so each point on the temporal profile of the pulse propagating at different speed. So you will see some tilt on the pulse. It's modeled by this variation, as you see here, the variation of the amplitude of the field with propagation distance. It changes with the variation of the intensity times the field. And as we said here, there is no imaginary part. That's why the effect for this one comes to the temporal profile. If you recall the equation for the cell phase modulation or cross phase modulation, you will find J. You will find the imaginary part. That's why this effect comes to the spectrum, but this one comes to the temporal domain because here how to model it, we model it in terms of linear, in terms of real part, I mean. Okay, So here is where is the example? Okay. Okay, the example is here. Okay, let me just launch the example first to see it. Thank you. We don't have anything. We don't have any problem. We just launched the OptiSystem one. Here is the program, the OptiSystem program I created for you. If you look at this one, if you look at the nonlinear one, self-steepening. Let us check the self-steepening. Okay, and if you go run it, it takes around few seconds. It's not that much, so I don't need to repeat it again. We have medium propagation, we have auxiliary components, we have another auxiliary component just to visualize the results. This optical domain and then time domain, I think it's done. So let's go to check. This is the dual port optical time domain visualizer. So you can use single port or dual port. Dual port just to compare between two signals. So if you see here, one input, it's connected to the output of the nonlinear optical fiber. Sorry, this is the input because it's I connected from right to left. So this is the input of the optical fiber, and this one is connected to the output of the optical fiber. So if you compare between the two signals here, we have 20 iterations just at different power level or different power level. Yes, let me just, as you see here, the effect of the self-steepening, there is some tilt on the output pulse, and the peak itself goes up. And I didn't include the attenuation. That's why the peak goes up, because the pulse width, there is no energy loss. So from the energy conservation principle, so if the peak goes up, so the width has to decrease, so just to keep the total energy the same. If we continue with this one, so the self-steepening cause what's called optical choke, because the peak itself goes up and up and up until you have something like optical choke. Okay, so I think now this is good. Let me check it. Okay, I think now it is good. This is the parameters. This is the parameter of the power. I changed it just to study different effect of the self-steepening, and as I said, you can change it with different values. And this is the result. You see it at different values of the power. So as you see, the tilt increase with the power. Here power 300 and here 400. You see the big power increases and the tilt increases. Okay, here now we're gonna stop to take a few break and to answer your question. Brian, you can take the mic. Thank you.
Thank you very much, Mohammed. I'm going to go ahead and launch the second poll while Mohammed has a chance to read through the questions. And again, this is one of the best times to ask is midway. If you have any questions on the first half, we'd like to get those questions out now. We will have a second Q&A period at the end of the webinar, so you can also ask your questions at that time. And also, if you have anything that you'd prefer to ask us just directly via email or give us a call, you can do that after the session. That's fine. We're available to answer any questions that you guys have. And just to reiterate it as well, we will have the recording of the webinar go out. It goes out exactly 1 hour after the webinar ends, so you should have it in about an hour and a half from now. With that said, I'll go ahead and close the poll and hand it back to Mohammed.
Okay, thank you, Brian. So let us continue with the rest. So we already done with 3 examples. We have another 4 examples. The first one is 4-wave mixing. 4-wave mixing, actually, the main concept, we have 3 signals, and from these signals, they intermodulate to each other or interact and produce another one. We have 2 examples, special example. We verified these examples with our software, with our OptiSystem software. So the first example is published in this reference. I left the reference by the end of this one. We have 2 signals, new 1 and new 2 with different frequencies. And due to the 4-wave mixing, there are another 2 signals generated. The first one, it's generated as 2 new 1 minus new 2, and the second one 2 new 2 minus new 1. This reference explained this one, and we verified it with example I will show to you. Another example, it's in Agrawal book. Here he said, Agrawal in his book, he said, if you have a very powerful signal, only one signal, very powerful, this signal will generate two sidebands, will generate two signals symmetrical to the source, to the original signal, and we verify this as well. Okay, let's go to this one. Okay, thank you. We are accessing our software. Okay, so let us start with the two signals. The first example, as I explained to you, we have two we have two signals here. The first one, it's centered at 1540, and the second one is centered at 1540.5, and both have 1 milliwatt. And we combine these two signals together, and we launch the combined signals into nonlinear optical fiber, and we let us run it to see what's going on. So I run the two layout. It shouldn't take that much. It should take 15 seconds or 10 seconds as well. Okay, that's done. Okay, let's go to the two signals here. As I said, if you check here, the two signals are combined. Optical spectrum analyzer to the fiber, we have only two signals. And if you check the output, here is the nonlinear optical fiber. Here is the output. Okay, so you have here new one and the new two centered at 1540 and 1540.5, and we have another two signals. As you if you calculate the center frequency here, it will match perfectly to what's written in this reference as a proof of its verified results. Okay, so let's go to the second example, the second layout. This example, it's a concept. It's written, as I said, it's written in this first reference, and it said if you have only one. So I tried here to increase the power for the first signal and put the second signal almost zero. So we have only one signal here. So if you check here, so the input is only one signal, because the second one, it's 100 dBm. As you know, zero cause a lot of problem with the numerical calculations. So 1 minus 100 dBm, it's equivalent to zero. Zero signal, it means there is no signal. And if you check the output of the nonlinear optical fiber, you will see here wow, you will see here we have a very powerful, yes, don't forget, I increased the power to 35 dBm. You will see here two signals. There is two signals generated beside the original one. Okay, so this example is done with the 4-wave mixing. Okay, thank you. Okay, so as usual, just I summarize it in the presentation to be able to reproduce it if you want before we send it to you. Okay, so this is the structure. This is the two signals example first, combine it and launch it. And this is the input and this is the output. This is the second example. We have only one signal. The second one is minus 100 dBm, and we got the output. This is the input and this is the output. We have another two signals to verify our results with the published literatures. Okay, let's go to the scattering part. We have three examples of the scattering part. The scattering part, it means there is interaction of the light with the structure of the medium of propagation. As we said, we have two kinds of scattering. The first one is inelastic. It means the frequency of the generated signal, it's not the same as the frequency of the source, and elastic, the frequency would be the same. So this one really backscattering, it's the same one, it's elastic one. It's modeled only by the back reflection coefficient. So imagine now we have a forward signal. Forward, let us put a reference like the forward signal. It means the signal propagating from left to right. So the backward signal, it's signal propagating from right to left. So here, the generated really backscattering signal, if we have it from left to right, so it will be from right to left. And here is eta, the relay backscattering coefficient. And this is the two equations relate the forward and the backward signals. Okay, let's go to the example and we'll summarize it. Okay, we access our program. Okay, so we have here two we have here two layout. It will take around 30 seconds. It's not that. Okay, let us start with it. Let us start simulation at first, and after we can see the results. The first one explain the phenomena itself, and the second one explains the effect of this phenomena on the performance of the system. Okay, so it's okay. It's done. It's 17 seconds. Good. Okay, let's go to the description itself. As we said here, we have this nonlinear optical fiber. It's a bidirectional one. So the signal, it's coming forward from left to right. So I checked the backward direction here. That's why I call this one a spectrum of spectrum analyzer of really backscattering spectrum. So if you check here the spectrum of the input signal, here it's centered at 155. So and the back one, it's centered at 145, and it's a parameterized signal. As you know, the OptiSystem can deal with different kind of signals. Sampled signal, it means frequency, and in time domain. Parameterized signals, we took the average and it's only treated in frequency domain. Okay, and the signal here of backscattering, it's centered at the same frequency. That's why it's elastic scattering. Okay, let's go to the effect for this backscattering, because backscattering, it's considered as some sort of losses. So that's why it would affect the performance. So if you look at this one, of this curve, just I changed the relay scattering coefficient, and I see the parameterized signal, the back losses. So it increases with it. So someone was asking about how to plot this curve, so I can reproduce it here again. Let me answer the question and reproduce this one. So as you see, okay, I didn't say. So you can here insert a grid, like to insert some data, or you can insert a graph like this one. So after you insert a graph, you have to define the x-axis and the y-axis. If you recall the layout here, what my x-axis, okay, no, it was the relay scattering. So it's one parameter of the fiber. So I will go the fiber, the nonlinear effect of the fiber, it's relay, so it's enhanced. So it's this one. So I change it with all these values. You can change with linear, exponential, whatever you want. And I close it. So it's really backscattering. So I will come to my graph, and I will come here to the left-hand side. It was in nonlinear optical fiber. I will open it. It's one parameter of nonlinear optical fiber. And I was trying to get this Brillouin. It's called relay scattering. Relay scattering. Okay. Okay. Okay, so I just forget to say, because I didn't find it here. As I said, I have two layouts. So the first layout is description. I was looking for it in the description, and that's wrong. I should close it. I should look it for the system performance. So I will go to the nonlinear in the second layout. So just make sure when you have more than one layout, just to go to the correct one, go to the nonlinear fiber, the parameter one, and go to the relay backscattering. This one is the variable. So I will drag it and drop it here. So, okay. It's dropped here it's dropped in y direction. Okay, let me make it very fast with this one. Okay, it's here. Okay, so by default, this value is plotted as a function of the iteration number. We have 30 iteration number, but I want to plot the parameterized signal power. This parameterized signal power, just let me remind you, it's measured by the optical power meter relay scattering power. So I will go to the report. Don't forget to choose the correct layout. Let me close it just to minimize the area of researching. It's optical. It's here. Relay and its results, and it would be the power parameterized signal. Okay, let me just see here. parameterized signal power. Okay, so I selected the second one. I just drag and drop it, and don't forget to put it in Y direction. You will get the same figure. So I hope I answered this question. So just let us little bit speed up with the other example. So in this example, just we studied the relay back scattering. We have another two examples. So we're done with this one. As usual, we have some figures just to help you to plot it or to build your own project. If you don't have this new one, you can use bidirectional optical fiber, and don't forget to put the dispersion and the polarization mode dispersion to 0. Okay. Okay, stimulated Raman scattering. Stimulated Raman scattering is some sort of scattering, but in this case, it's elastic one. So it means there is some variation in the domain itself, and the generated signal, it's not the same as the source itself. So it's an elastic low wavelength signal transfer power to longer wavelengths. It has different effect. One of them is what's called Raman tilt. Raman tilt, it means, as you will see in the example, the low wavelength signals will transfer power to the longer wavelength signal, and you will see in WDM systems there is something like a pyramid or something inclined. Okay, it's modeled by different models as well. One of them, just here I just use the Raman gain coefficient only, and all the other nonlinear phenomena it's neglected just to focus on this one. So as you see here, we have a forward power and we have a backward power and we have Raman gain coefficient. This Raman gain coefficient is function of the frequencies, the difference between the frequencies of the forward and the backward power. And we have here polarization factor, and for sure its effect of the cross-section area. This cross-section area is a very important parameter in nonlinear phenomena. Okay, let's go to the example just to see what's going on in this one. Yes, as usual, there is no issue. We just access executable file. I created here a very simple program. Just I have a WDM. I have an array of laser sources, and these laser sources inserted in the nonlinear optical fiber, and we have optical spectrum analyzer on the other hand side. Okay, so let's run it. It takes around 40 seconds, so we have time just to explain whatever we want. I had to say something about if you have a bidirectional component like this one or bidirectional optical fiber, and if you want to make only unidirectional experiment, you have to put a null on the second input. You have to put a null. Otherwise, the program will not give you a correct result. So just for bidirectional one, make sure to put a null if you want just to simulate a one-directional experiment. Yes, I think it's done now. If you compare between this is the input spectrum. Just let me zoom in a little bit just to see it. Yes, by the way, you can zoom in by right-click and check zoom and choose whatever you want here. And just so as you see here, the WDM, all the signals, all the carriers have the same power. If I check this, let me leave it. So the optical spectrum and the input to the fiber, let me check it, the output here. So the output here, the sampled, the parameterized signal here. So I will make zoom in, like right click, as I said, just right click and choose zoom. And here, wow, look, here is the difference, big difference between the input and the output. What happens here due to the Raman effect? I will show you for sure. I checked here the optical fiber in nonlinear one. Raman is not here, it's in enhanced. Yes, sorry, Raman is here, Raman is scattering here. I checked it, and you can insert Raman in different way by choosing. You can insert your own data about the Raman gain coefficient. You can insert it in two different ways, as a Raman gain efficiency or as a Raman gain. Or if you don't have a data, there is some built-in data in the program. So just you have to choose whatever calculate. Here, Raman gain or calculate, so the program will use the built-in data it has. Okay, so this is phenomena. Okay, let's come back to the analysis of the output. See, here is the output, here is the input. If you compare between it, so it's very clear the low wavelength part, the wavelength part donate some energy to the high wavelength carriers, and this is very important, or very like it causes a lot of problems. Imagine you have a WDM system, and signals carried on the low wavelengths experience a very attenuation part, while the longer wavelength parts get some energy, and it might experience another kind of nonlinear effect. So this phenomena comes from the Raman effect. Okay. So I think now we only, I'm sorry if you got tired. I know it's a lot of information, but I was trying to make it as comprehensive as I can, just to be a revision for you and for me as well. Just if we want to start something, we can use it to start your project and just come back to analyze it. Let me just have a cup of water. Okay, as we said here, I just give you in the slide, this slide, the data that you can use, and this is the result for your information. Okay, this is the last one. The last example that we have is stimulated Brillouin scattering. Stimulated Brillouin scattering is some sort of scattering. It's an elastic as well. Its bandwidth, it's very low. That's why it doesn't cause cross-coupling effect in WDM. And the difference between the generated signal and the source itself is around 11 gigahertz, and it's backward. So how can we model it? It's modeled in reference number 4. So you will see here, this is the bump, and this is the signal itself, and the bump has a frequency at certain frequency nu, and the signal, it's frequency minus 11 gigahertz. And this is the relation that couple the intensity of the bump and the intensity of the signal. Okay, let us very fast go to the program just to see it. And after here we have two, as usual in the whole examples, we have two. One, okay, it's take little bit more time. It take around 1 and 15 seconds. Let me run it. And as you see here, I have two layout. The first one to describe it, and the second one just to study the effect of this phenomena on the optical communication system. In terms of the most important one for me, as for you, you can change whatever you want, the quality factor of the system, the bit error rate, the eye opening factor. There are many other factors that you can play around it, and you can study the effect of any phenomena on the optical communication system. Okay, it's done. It's done faster than I expected. Okay, so okay, if you look here, this, as I said, it's a backscattered one, and there is 11 gigahertz frequency. So just let me check with you if I forgot to check the Brillouin scattering or not for enhanced. Yes, I checked Brillouin scattering, and I put some data for the Brillouin gain constant. So the result will be as a result of the Brillouin scattering. Okay, so if and I said it's backwards, that's why I call this one stimulated Brillouin scattering. Let me check it. Okay, so I have a signal here. Let us check the signal. As I said, it's 11 gigahertz apart from the original one. This original one, it's around 193.4144. So let us go. We can add a marker just with right click, and we can trace this marker with layout. Just let me increase the window just to be able to see what's going on here, and I will come back with the marker. And when I put a marker at any point, so I can see it here, let me just by my hand, I hope I catch something. Okay, so this is the frequency now of the signal. It's around 193409 10 to the power 14. Here is 1 0.93444144 10 to the power 14. So if you subtract these two values, you almost find 11 gigahertz difference. So that means the signal is coming from the brilliant scattering one. I don't know. I have another one for the system performance. Okay, yes, the same one. You see the quality factor, the opening factor decreases as well, and the bit error increases. Here you will find a lot of fluctuations. You can decrease the step just to get a smooth variations, or you can just study something new. Okay, I think now I am done with all the examples. Okay, this, as I said, this is the summary for what I have. Let me finalize the webinar with something interesting for you, just to leave you remember all this stuff. What we have done here in this one, we have studied self-phase modulation. The self-phase modulation, the signal itself increases its spectrum. Cross-phase modulation, we have mutual coupling between two signals, one affects the other. Self-steepening, temporal tilt, the effect for the self-steepening is temporal tilt. Four-wave mixing, generate new frequencies. Backscattering, really backscattering, it's loss mainly. And Brillouin scattering generates signal 11 gigahertz apart, and we have stimulated relay scattering cause Raman tilt. Let me show you some stuff. I collected all the data in a movie just to see how the signals, this signal, the input comes, and the signal now is propagating inside the fiber, and you can see all the iterations now in a movement, just in animation, just to see how this animation shows the the self-phase modulation broadening due to the spectrum broadening due to the self-phase modulation. I have something for cross-phase modulation as well. We have the time, and we have, let me explain to you just to remind you, we have two signals, and these two signals apart from each other. This is the temporal domain, and this is the frequency domain. This is the output. And as you see, the bigger one has a self-phase modulation effect, and the second one, it doesn't have it, but with delay, you will see this one moves on the second one just to see it. So there is no effect. There is no effect until the bigger one, the powerful one, start to overlap. Just watch this one. You will see change in the spectrum and go until it get rid of it, and you see the dynamics of the spectrum. For me, it's very interesting. I don't know you will agree with me or not, but most probably we'll add this feature to the OptiSystem very soon. Let us know if you like it. And the self-steepening, I have another one for self-steepening. So the new one, so imagine this one is the input one, and the second one is the output at different power. So you will see how this self-steepening makes the peak power increases and the pulse width decreases. And if it continues with the system, it might cause optical shock. Okay, and the last one, the Raman tilt. So here we have the input. I got the input is flat, and after the propagation of the WDM system, you will see the low wavelength part donate some energy to the high energy part. This is increasing and this decreasing, and cause a lot of problem in WDM system. Okay, I think I'm done now with all the presentation. I left the reference for you here. If you want to read more, there are a lot of reference, but this reference, it's very powerful for us just to verify what we have. I have a lot of questions here. Okay, so I will give Brian just to start the second poll until I read some of your questions and come back to you. Brian, you can take it. Thank you.
Thank you, Mohammed. Okay, so we're going to go ahead, put the third poll up for everybody. And those that have attended previously, I mean, these are the same polls we've been asking, but they're very useful for us just to understand what the audience is that's attending these different sessions. So again, your participation in them is greatly appreciated. And as Mohammed suggested, there's quite a few questions that are that have been asked. If we can't get to all of them during the actual session, like live, then we're going to go ahead and take these questions and email you afterwards the replies. And of course, some of them are also a little bit more in depth and require a more detailed explanation regarding the answers. So for those as well, we'll take those offline and answer you directly. So I'm going to go ahead and close the poll. Hopefully Mohammed had a chance to read through some of these questions. I'll go ahead and pass it back to him.
Okay, Brian, thank you very much. I will answer some of the questions here, and if you have more questions, you can send it to us, and we'll come back to you as soon as we can. So one of the questions, he said, there is some threshold for the Raman effect for sure. All the nonlinear phenomena, each of them had a threshold. Once you exceed this threshold, the nonlinear phenomena will appear. Okay, so another one, he said, how can we relate the CW, I guess it's a chromatic dispersion, and the chirp to self-phase modulation and the cross-phase modulation in the previous example? Yes, as I said, yes, chromatic dispersion in the new component, we just focus on the nonlinear parameters. But if you want to insert the dispersion, you can use the bidirectional one with the same settings, and you can insert the dispersion you want. It chirp, there is a component in the OptiSystem just to check the chirp. There's a component called, let me try to find it if I can. Just, I will open any example here. Just, and you can check and you can study the chirp. And there are some examples, just remind me and I can send you example just studying the chirp. So if you write here, yes, by the way, if you want to access any component, so with the left hand side, with left click, with right click and find the component, and you can write whatever you want. So let me write a chirp here and search. So optical chirp detector. So with optical chirp detector, so just take it and see how can you connect it, and you will be able to detect it. How can we? I think I can answer the other questions by email. And just I want to remind you with two things. If you have any questions, just send it to me, and we will come back to you as soon as we can. Another point, if you feel like there is any topic we need to make a webinar, just let us know. And based on the statistics, based on your requests, we can prepare another webinar. Thank you again very much for joining us in this webinar, and see you later. Brian, you can take it. Thank you.
I think that's all good. The email address to send any questions to would be support@optiwave.com. And then everybody on our support team will get those. So thank you very much for attending, and we'll be having future webinars coming up in the probably 2 or 3 weeks from now. So please check the webinar section of our website to keep informed. Have a good day.